Syntax builds the form we see. Semantics gives it meanings key. Connectives link what minds devise. Quantifiers range through truth and lies. Modus ponens strikes with might. Modus ponens flips the fight. Logic cuts clean, no shallow line. Through the long night, reason shines.
Previously, we saw how predicates become formulas when applied to variables. When the domain of discourse is infinite, we need more than just logical connectives to express certain propositions. These additional tools are called quantifiers. For now, we will consider only predicates that involve a single variable. More general cases involving multiple variables will be discussed later. A quantifier is a logical operator that tells us how many objects in the domain of discourse satisfy a given formula. There are two standard quantifiers: the universal quantifier, written as for all. It can also be expressed using phrases like for any, for each, or every. The existential quantifier, written as there exists. It can also be expressed using phrases such as for certain, for some, or at least one. As the shapes of these symbols suggest, the universal quantifier looks like a vertically reversed letter, A, which relates to the word all, and the existential quantifier looks like a horizontally reversed letter, E, which relates to the word exists. Given a formula Px, we can use a quantifier to bound the variable to form new propositions. Syntactically, we put a quantifier, either the universal quantifier or the existential one, right in front of the formula Px, which reads, for all x, Px, or there exists an x such that Px. Semantically, suppose the domain of discourse is a set D. The truth values of these quantified statements are assigned as follows. The statement for all x, Px, is true if Px is true for every term in the domain. Otherwise, it is false. The statement for some x, Px, is true if Px is true for at least one term in the domain. Otherwise, it is false. From these definitions, we immediately see the equivalence. The negation of for all x, Px is logically equivalent to there exists an x such that not Px. Similarly, the negation of there exists an x such that Px is logically equivalent to for all x, not Px. For example, consider the domain of discourse to be the set of all cats, and let Px stand for the formula x is a ginger cat. Now consider the statement for all x, Px. This reads, every cat is a ginger cat, which is clearly false. Its negation then reads, not every cat is a ginger cat, which is logically equivalent to some cat is not a ginger cat. This statement is true. Also note that if you simply change the quantifier without negating Px, you get for some x, Px, which reads, some cat is a ginger cat. While this is also clearly a true statement, it is not logically equivalent to the negation of the original statement. In many cases, we are only interested in the truth of a formula when it is applied to a subset A of the domain D, rather than to the entire domain itself. We sometimes refer to A as a subdomain. In such situations, by a common abuse of notation, we write for all x in A, Px, to mean for all x, if x is in A, then Px, and we write there exists some x in A, such that Px, to mean there exists an x, such that x is in A and Px. We have already seen for all x, Px, and for some x, not Px, are negations to each other. With this in mind, using standard logical equivalences, we can generalize the previous result to negation of a quantified statement over a subdomain. Briefly speaking, here are the three steps. Step 1. Keep the set A unchanged. Step 2. Flip the quantifier. Step 3. Negate the formula Px. To see an example, let the domain of discourse be the set of real numbers, and let A be the set of rational numbers. In this context, since it is well known that square root 2 is real but not rational, the statement, the square of some real number is equal to 2, is true. On the other hand, the statement, the square of some rational number is equal to 2 is false, whose negation reads, no square of a rational number is equal to 2, which is true. We have now learned the basic concepts of the two distinct quantifiers, as well as formulas formed using a single quantifier. For the purpose of deduction, we will need some rules of inference related to quantifiers, which we will discuss in the next section.
信了，ten say。